Hello, welcome and happy Global Geothermal Awareness Day. I'm so excited. We have an amazing program. And I just want to say thank you for everyone for registering. We have a really, really great turnout in terms of registration. And I just want to say this is the second of a three-part geothermal series sponsored by Halliburton. So thank you very much to Halliburton. And also want to say thank you to our speakers, Joshua Webster, who is the lead for artificial lift discipline, and also for to Gabe Matson, who's the senior exploration lead for geoscientist for Fervo Energy, and also to Nicole Wagoner, who will be talking to us in a minute, who is also our president of the Geothermal Committee for the Energy Minerals Division. So before we get started, just have a really quick poll question. So I'm going to launch it right now. Okay, so will you be attending the 2025 Geothermal Rising Conference, October 26th to 29th in Reno? So anyway, everybody's answering. And while they're answering, I just want to say that if you have any questions, please put them in the Q&A box and we will answer them at the end of the session. And also I just want to have a minute to ask you if you will like to be a member of the Energy Minerals Division, please go ahead and join. And thank you. And it looks like we have a pretty good response, and few people are responding, but I'll go ahead and end the poll. And I'll share the results. So it looks like some people are planning to attend. That's good. And I'd like to encourage more people to attend. So right now, I'd like to turn the screen over to Nicole Wagoner, who is going to talk to us a little bit about the Geothermal Committee.
Yeah, thanks, Susan. Let's make sure that I can change the screen. There we go. Yep, as Susan said, the APG Geothermal Committee is a partner in putting some of these webinars together. So we thank you all for letting us share our expertise. So the AAPG Geothermal Committee is part of the Energy and Minerals Division of AAPG. If you're interested in joining either one, you can go to the AAPG website and find the Energy and Minerals Division as well as the Geothermal Committee. I am the chair of the committee. I also get a little bit of help leading the committee from David Wallace, who's my vice chair, and Gabe and John are helping out with our technical events, and Mayank is our Gulf Coast representative. So the committee is kind of focused on a number of different things. Kind of our main objectives are putting together technical events for conferences, workshops, and webinars like this. We also work on online engagement through LinkedIn, hoping to also get an AAPG Wikipedia page started. We're also looking at communications such as annual reports, newsletters, Explorer articles, things along those lines, and outreach within AAPG and externally with other groups as well. So if any of those sound interesting to you, go ahead and scan that QR code, the first one that says join the committee, and you can hear a little bit more about what we're doing and what our plans are. We're also looking for other folks to help out with leadership in other leadership roles, as well as section and region representatives. So if you're interested in volunteering or helping out with the committee, there's a second QR code there with volunteer under it. So you can go ahead and scan that and fill out those forms, and I will get your results from your form and be happy to include you in our future work. So with that, I'll hand it over to Gabe to kick off the technical webinar.
Thanks, Nicole. Hey, everyone. My name is Gabe Matson, and it's my pleasure to present to you all today a case study of subsurface characterization for an enhanced geothermal system at Cape Station in Utah. As a little introduction to myself, as Susan mentioned, I'm a senior exploration geoscientist at Fervo Energy. And with a background in geophysics and geology, I've been working in conventional hydrothermal and enhanced geothermal systems across the US and internationally, starting back in 2015. And the work I'm presenting to you today has been a massive collaboration between geoscientists and engineers and others across Fervo and our partners. And it's just simply my honor to be the one presenting it to you today. So with that, oh, there we go. Hopefully not too many slides go by. But so just a little bit of a roadmap of what we're going to talk about. First, I'll give a brief introduction to enhanced geothermal systems. I'll give a little bit of an overview of Project Cape. I'll go through a few of the surface studies that we've used to help constrain our models, and then finally kind of go through the integrated 3D geologic and temperature models. So just sort of as a background for everyone, I wanted to give an introduction to what is an enhanced geothermal system. So in conventional hydrothermal systems, we're looking for natural permeability that's hosted in faults and fractures and permeable rocks that can host hot geothermal brine. In enhanced geothermal systems, they're a bit different. We still make use of that underground heat, but we use stimulated fracture networks for permeability rather than the naturally occurring permeability. And this technology helps unlock geothermal power potential in areas that are unavailable for conventional hydrothermal projects. And what does that look like? Well, in Fervo's case, we drill vertically, as you can see here in the, we drill down vertically, in our case, about 8,500 feet at Project Cape. We turn and we drill a lateral, which is about 5,000 feet long. And then we have engineered fractures that I was mentioning to enhance the reservoir permeability and connect the injection and the production well. Then we inject fluid down our injection well. That fluid travels through those fractures and heats up as it makes contact with the hot rock. And then it's brought back to the surface through the production well, where it enters our heat exchanger and heats up a working fluid, which then is used to spin a turbine and generate electricity. And then the geothermal brine stays in its brine state. So 100% of that geothermal brine is then re-injected back into the injection well. Great. So just a little overview of Project Cape. If you're not familiar, this is a map of Utah in the western US. Project Cape is in southwest Utah, which is about 4 hours south of Salt Lake City. Project Cape is adjacent to a DOE-funded Utah Forge project, which is also an enhanced geothermal research project. And it's in the same basin as the Blundell geothermal field, which is just east off of the map here. Project Cape is currently planned for 500 megawatts of production over 2 development phases, and with 100 megawatts being phase 1 coming online in 2026. And sort of to date, we've drilled, actually, this map has 18 wells. To date, we've actually drilled 24 wells, but we've drilled these 18 horizontal wells and 1 vertical monitoring well here, Delano 10B. And these horizontal wells have been placed in 2 benches. So you can see here's a cross section south to north across all of our pads. And we have sort of this upper bench, bench A, and a lower bench, bench B, with an average of about 200 degrees Celsius at the heels of the wells and about 220 degrees Celsius on average at the toes. And the wells alternate between injectors and producers as you go from north to south. So that's just kind of a general overview of what the project looks like. But we're going to take a step back now and look at a selection of surface studies that that we use to characterize the subsurface along with the drilling results. So first up is gravity, and probably many of you are familiar, but if you're not, gravity is a standard exploration tool that's used to map basin structure, intrusions into sediments, hydrothermal alteration, and fault structures. And the gravity survey, which when you're actually acquiring it, looks like this. You have someone with their gravimeter measuring the gravity, and then you also have a high precision GPS unit to get really accurate location information. And you're measuring small changes in the acceleration due to gravity across your survey area, and those changes can be attributed to different density contrasts in the subsurface. And you can use those to infer something about the subsurface geology. So at Project Cape, Fervo acquired 1,388 new gravity sites back in 2022. So that's the blue dots on this map. Just to orient you a little bit, this is the Frisco pad. So that was our first horizontal pad that we drilled. And then the Forge project is here. That Blundell geothermal field is these wells up here in the foothills of the Mineral Mountains. And then there's also a Wildcat well that got drilled, sort of a legacy well out in the middle of the basin. Our station spacing was about 250 meters in the core of the survey area, and it expands to greater than a kilometer out in the fringes. Along with the data we collected, we also merged our data with about 280 stations that Forge collected and about 425 stations that were sort of legacy data through the Pan American Center for Earth and Environmental Studies, PACES. And the gravity was processed to a complete Bugig anomaly using a 2.45 grams per cc reduction density. And I'll just point out a couple of the trends that the gravity data is showing us here is, we have a sort of a deepening basin as you go west from the Frisco and Forge pads. But also there's sort of this north to south trough that deepens as you go from north to south, with the projected deepest point in the basin sort of being around this area. So how do we actually use this to infer subsurface geology? Well, we use a few different gravity modeling techniques. So first we used a fairly standard technique of gravity forward modeling, where gravity forward models were constructed and calibrated based initially on the Forge wells, density logs. But our wells, our Delano and our Frisco and subsequent pads were drilled through a deeper, alluvial package. And so after drilling our Delano well, we collected a density log, which you can see here to the left, overprinted on our lithologies that we encountered. So the density log is here in red. And we use that density log to help calibrate our gravity forward models. And then subsequently, with each new pad we drilled, we also used those density logs, and that just gave us better, better accuracy and confidence in our modeling. And we use those to interpret our top of basement along with some of the basin fill packages that you can see here, and the granitic basement is shown here in purple. And up at the top here, these black points are the observed gravity, and the black line is our modeled gravity from this forward model. So you're trying to get as close of a fit as possible. And so to help constrain our model, our granitic basement top, we use 7 gravity profiles, east-west gravity profiles, and 2 north-south tie line gravity profiles. And that new 3D basement model was used to predict the granitic basement contact at the Frisco wells, for example, with very high accuracy, so less than 100 feet. And since then, in addition to the 2D forward models, we've also performed 3D inversions of the gravity using multiple inversion methods, including GMSys 3D and Viridian's RLM 3D. So we're trying to get as much out of the data as possible. Also, another important data set we're using is 2D, and actually this should say 2D and 3D seismic. So we have access to legacy 2D data, and Forge also collected 2D and 3D data. So this red box here is Forge's 3D seismic footprint, and then these red lines outside the box are 2D lines. And I'm showing here 2 different profiles. This one down here is from within the 3D volume, and you can see the top of the granitic basement is interpreted and is quite clear, at least within the core of the survey area. You lose it sort of on the edges here. But then a lot of these 2D lines that go out into the basin, as you can see from this image, they sort of lose the top of granite. But they do have a good image of the overlying basin fill, including some volcaniclastic packages. And those are, tied and correlated to the Accord-1 well. So another key method we used to characterize the subsurface here was magnetotellurics. And magnetotellurics is a passive electromagnetic method that uses natural electromagnetic signals over varying frequencies to measure subsurface electrical resistivity, which can be used to interpret different lithologic horizons. So to give a little bit of background on this image, the colors in the background here are the resistivity. Warmer colors are lower resistivity, and the cooler colors are higher resistivity. And then you're seeing the Fervo wells here. So this is our vertical Delano 10B, our Frisco wells. You have the Forge wells here, and that Accord-1 well that we've been discussing. And then next to our Fervo wells, we collected methylene blue. So it's a little hard to see, but this track here is the methylene blue measurement down the well. And so you can see there's sort of elevated methylene blue right in this area, and I'll talk about that in a second. But so while we were drilling Delano 10B, we encountered this pure spectite clay, which we noticed in the cuttings, and it was confirmed with that methylene blue analysis. So that's where you see elevated methylene blue is correlated with those smectite clays, which is that little gray unit along the well track. And so we used the Forge collected magnetotelluric stations. So that's all these black triangles at the surface. But we performed depth limited 1D inversions on that data, targeting to resolve the shallow resistivity patterns. And previous MT studies had been done, such as Wanamaker et al. As part of the Forge project. However, those were 3D inversions that were really focused on deeper resistivity patterns. And so the 1D actually does a really good job of resolving this thin, shallow, low resistivity zone that correlates remarkably well to the clays that are identified in both the publicly available mud logs for Accord-1 and the Forge wells, as well as our drilling results that we saw at Cape. So we use this correlation to create a 3D clay model, which you're sort of seeing a rendition of up here, along several profiles, to predict the clay depth and thickness, and we've used that to a high degree of accuracy. This has helped plan constructions and anticipate drilling risks ahead of time. And aside from these 1D inversions, we've also done 3D inversions of the MT data that have helped our geologic model. Great. So what does that look like when we integrate everything together? Well, here we're looking at two cross sections through our well field. So obviously here's our well field in this map. We have an east-west section, which is down here, and a north-south section that goes through the wellheads, excuse me, to the left. And you can see sort of what we were looking at in that gravity profile, but you see the granitic basement as you go from east to west, sloping down into the basin. You see these basin fill packages, including this orange layer, which is volcanics and volcanoclastics, a yellow basin fill sediment unit, and then that gray clay unit that we were just talking about. And so even though there's a high degree of dip on that basement surface in the east-west direction, when we look at it in north-south, it's relatively flat. And that makes sense. You're sort of going along the trend of the basin. And this has been beneficial to us because it's allowed us to target a rack of horizontal wells along the basin with a fairly consistent top to the granitic basement. It's allowed us to standardize well design and bit selection, and helped us reduce subsurface risk. And I'll also point out, although the granitic contact is fairly consistent across all our wells we've drilled, the overlying basin fill is not necessarily that consistent. For example, you can see in this sort of beige color, this is a welded tuff, where at Frisco, we experience these sort of thin lenses of welded tuff, and also in the bearskin pad to the north. But in our central pad, the gold pad, we encountered about 2,300 feet thick welded tuffs, which we attribute to, essentially volcanics that were deposited in a paleo channel during, Miocene eruptive events. And that paleo channel would correlate fairly well with there's a current existing channel, major drainage that comes out of the mineral mountains right about here. So even though we see some of these major differences in the basin fill package, it's not necessarily a concern for us. These tuffs haven't had effect on our drilling performance, and they don't present hazards to our drilling performance. And once they're drilled, they are positioned behind an intermediate unperforated casing. So more of a geologic interest than necessarily a drilling risk. So then, to talk about some of the other features we're looking at here, the temperature model. So looking at these same sections, you see our temperature contours here in dashed red lines. And these were built using existing temperature logs from Forge and Blundell, and Accord-1, along with statistically derived temperature gradients where we lacked well data. And the resulting 3D temperature model shows a couple different features. One is are these elevated temperatures here near the Blundell field, where hot geothermal brine is convecting up these eastern dipping normal faults, coming closer to the surface. As you go out into the basin, the temperatures are slightly depressed relative to Blundell, but they're still elevated. You're getting lateral conduction of those temperatures from the Blundell field, you're getting higher heat flow because you're in the basin and range, and you have sort of thinning crust, and also you're getting sort of an insulating effect of these lower thermal conductivity basin fill sediments relative to the granite. So that's all also anchored by our Acor 1 well, which we've encountered, or it's reported to have encountered 175 C at about 9,000 feet. And so I'll also comment on when we look at it in north-south, sort of similar to the top of granite being relatively flat, our temperature contours are also relatively flat. There's a little bit of fall off to the north as you get further from the upflow of the Blundell system, but it's not very dramatic, and it allows us to have relatively flat benches here. And we've confirmed our pre-drill temperature model with temperature logs in a majority of our wells. So yeah, I'll move on from that. So we use all of this data to build out these 3D models with significant inputs from the surface studies that we talked about and anchored by the drilling results, of course. And on the left here this is a view of our 3D temperature model. This is the 175 C isosurface, pulling up here by Blundell. And then on the right, this is a 3D view of our geologic model, with obviously the granitic basement in purple and those basin fill packages above it. So yeah, as we've discussed, just in conclusion, these models have helped plan our development, target our lateral benches, design our wells, provide comparisons to the actual drilling results, and ultimately they're a living, breathing characterization of the subsurface that we are continually working on and using in everyday life at Fervo. So with that, I just want to say thank you, and I'm pleased to hand over the mic to Joshua Webster. Thanks, everyone.
Thanks, Gabe. Let me see if I can progress my slides here. Okay. Thanks, Gabe, for the explanation. My name is Josh Webster. I'm a mechanical discipline manager for artificial lift at Halliburton. Today, I'm going to talk about the benefits of ESPs and geothermal applications, and just give some considerations for the community to think about on the front end when trying to produce the geothermal water downhole. So first off, what are ESPs? So I'm going to explain what are ESPs, and then I'll go into a brief explanation of geothermal. And then I'm going to go to talk about some of our challenges in European geothermal wells, and specifically a few solutions to those challenges, which would be a development project on an intake component and then a development project on a pump component. And then I'll wrap it up. So what are ESPs? If you look at the illustration here on the left, ESPs stand for electrical submersible pumps, and they are completely downhole systems that have traditionally been a workhorse for oil and gas production. They come in many different shapes and sizes. Essentially, you can have a 3-inch all the way up to a 13-inch centrifugal pump downhole. And so these strings can be hundreds of feet long. We can go up to depths of 10,000 to 15,000 feet. The strings consist of a centrifugal pump that is powered by a downhole submersible motor. Typically, those motors are 3-phased AC induction motors. They can also be permanent magnet motors. We do have some ancillary components. There is a seal or a protector that helps protect the motor from the well fluid itself. We have an electrical cable that goes down hole, and so that connects the motor, which is 10,000 feet deep, to the surface electrical components. And you can also run sensors, which will give you downhole data. So the most popular component for these are a 4-inch, and specifically in North America. And this is for artificial lift to recover hydrocarbons downhole, boost production to the surface. This same technology, we can take that pump and package it on the surface in a horizontal piece of equipment that we call a horizontal pumping system. And that is used down in oil and gas. We're producing hydrocarbons, but a byproduct is a significant amount of brine or salt water. And so a lot of times we have to dispose of that salt water. So we will use the surface unit to pump back down. And so I really briefly wanted to give you guys an overview and then just explain that these technologies have really matured in the oil field, but they have a direct correlation and application to geothermal energy. So a quick introduction to some ESP use in geothermal applications. So geothermal energy is relying on the thermal energy that naturally occurs from the core of our earth, right? And so we're trying to harness that heat and use that to convert in for a few different reasons. Power generation, that heat can be harvested and used to spin a turbine to create electricity, or direct heating for municipalities. And so ESPs provide a good solution for these applications. So, and why do they do that? They have a relatively high flow capacity for the footprint you get. You can get a lot of flow out of these pumps. They have a low surface footprint, which is very important for a lot of these plants, and they are efficient for deep wells. So, ESPs can compete against vertical turbine pumps, but they have their own limitations when it comes to depth, because you have a surface motor with a direct line shaft to the pump. There's some depth concerns there. There's also concerns for operational flexibility. So a lot of those lead times for those type of equipment is very long relative to the ESP. Again, kind of referring back to the foundation that is oil and gas, these ESPs are pretty easily configurable. So we can take some core common components and then make alterations off of them for different applications. And so that really allows us to have a quick turnaround time and quick lead time relative to other solutions out there. When we compare geothermal to oil and gas, so what are some of the key challenges, some of the differentiators that we have to accommodate on the ESP? And so high temperatures are one of them. Geothermal energy is typically higher than some of the oil and gas applications we see. Aggressive chemistry, specifically, we'll get into this in a moment. The chemistry related to scale, and that's a function of heat and pressure. And then these applications typically require high flow and high power demands. And so that combined with temperature, there's kind of a competing issue there. The more flow you need, the bigger motor you need, the more horsepower you need. And typically when you add high temperatures, your horsepower has to be derated. You have to deal with that. And so all of that combined, reliability is extremely important. Downtime for these plants is something that's seriously considered, and handling the temperature is a challenge there. So this requires innovative solutions. So we have our own specific ESP design, and it's essentially a different trim level than what you'd see in the oil and gas, with designs that are fit for purpose for the geothermal market. And we'll discuss here in a moment a few of the evolutions of that, specifically related to application issues. So I kind of gave an overview of some of the generic differences. Now I want to take some time to talk about a specific challenge that that we have seen and we've come across through our time working within European geothermal wells. Gabe talked a lot about enhanced geothermal. So, it's kind of like a dry rock application where you have the thermal energy there, but perhaps the reservoir's not. The applications we have are more wet rock. So that is, there's a reservoir downhole, there's geothermal energy. So the hot brine or fluid is there for us to produce. And so that's where ESPs are very helpful. These applications, for the most part, are 13 and 3/8-inch casings. So that allows us to run some larger size equipment, 9.5-inch series pumps. There are applications that we come into that have tighter casings, but they have similar flow demands, so 9 and 5/8. And so that's one of the challenges we'll get into. These applications are looking for typically 30 to 50,000 barrels per day fluid for the plant's needs, and some can get up to 80,000. Horsepower requirements are somewhere in the range of 1,000 to 2,100 horsepower. Temperatures, typically these, we're seeing 120 to 170 C, but we have seen up to 220 C. And so those are things we've had to take into account in our design. Some of the specific issues that we're about to get into is completion quality. So as I kind of keep referring back to the oil and gas foundation, completions have matured there as well. So complete bottom hole completions with perforations, casings, that kind of stuff. That's typically where we operate in with ESPs. And as we get into these different geothermal markets, we kind of see that there's different maturity, different level of experience when the operators, different methods that are used. And that's things we have to consider, specifically open hole completions. Another issue is just the fluid and its harsh chemistry. We're finding that some of these are prone to scale due to the temperature and pressure we're seeing in the base fluid. And sometimes that's a challenge for some of these operations because the reservoir itself can be combined with water tables, municipal drinking water. And so you have to be very, very specific with how you control that. And so we'll talk about some of our navigations there. And then again, flow and efficiency demands. So something that is different from the oil and gas market is typically the ESP is a revenue generating device. In this scenario, it's more of a direct cost device. And so total cost of ownership, efficiency is top of mind in operational costs. And so we'll talk about how we deal with that. So first, I'd like to introduce, let's talk about the increasing reliability in open hole completions and scale. So specifically in one of the applications we're running in, we found that they had an open hole completion. So what does that mean? That means that you have a cased well until you get towards the end of the well, and then it kind of goes just to the formation. It's open hole. There's no longer a casing or cementing or anything like that to provide integrity. So in these wells, there's enough structural integrity of the formation that we don't have collapse, but what we've seen is there's significant particulates that come through our system from that, where maybe a more traditional completion would handle that. And so we had one application, 9.5-inch pumps, 50,000 barrels a day, where we were seeing a large amount of solids ingested through the pump, but also getting stuck in the intake of the piece of equipment. So that means we had trouble getting fluid to our pump. We were starving our pump. So much so that we actually, the power cable that runs down along this, we actually stoned it to failure due to these rocks coming through. So meanwhile, we tear down the pump, we find we've ingested solids. And that's nothing new for these pumps, particularly in oil and gas, but this isn't sand or proppant. This is more stones. And so those are a challenge. And so we're going to talk about how we address that. With that actually makes scale worse. So this application had calcium carbonate scale production, and it was scaling up the intake, it was scaling up the pump. We actually had, from that, you basically, with those rocks plugging the intake, you get a pressure drop. And so pressure drop allows, significant pressure drops can allow scale to come out of solution. And then we see scale attacking some of our critical clearances, particularly from a mechanical nature. Our bearing clearances, they can scale off, and then the rotating equipment will seize, and then you break a shaft. And so if you look at these illustrations, you can kind of see the different stones in the intake, the materials that were ingested into the pump. A lot of that scale can accumulate at the top of our protector, our motor protector, which can cause ingestion of, it can basically cause fluid contamination. And then ultimately we're seeing broken shafts from these. And so that's the challenge. Let's talk about our solution. So, traditionally, a lot of this can be done on the completion side beforehand. And so that's one of the reasons I want to discuss it, just to raise awareness. But we were already there. There was significant capital invested. And so we had to come up with a solution that was in the production string. And so we kind of borrowed from the completion side, and we created a fit for purpose geo intake. And so what this was is it had a perforated modular housing. We were able to increase the area flow, the flow area by like 5%. So increasing area, what that does is that allows for more flow into the intake. It reduces your velocities, which reduces your pressure drop. And so we did a lot of in-field testing as well as CFD testing to optimize the geometry of that. We found that a lot of the flow was accumulating towards the top. Even though we created a bigger area, it just wanted to go in at the top. And so we played with the spacing of our holes. We played with the size and the angling of the holes to basically distribute fluid flow into the intake. So that way we didn't see spikes in velocity and spikes in pressure drop. With that, we did a wire wrap around this perforated intake. And so this was borrowing from completion tools technology, essentially sand screen. And this helped us shield out those finer particulates that the pump ingested. And then particularly talking about the bearing failures and seizing the shafts. So we kind of modified the bearings that we saw there. So these bearings come with basically a lubrication groove that helps sweep scale out of there. And so we did a lot of optimization of that, going to more of a lobed bearing. We were able to increase fluid flow past the bearing by 5 times. And we were ejecting scale from our critical clearances. And then to tie all this up, we used a Teflon-based coating to prevent scale from even sticking. And then a special design screen. So if you look at the bottom of the intake over here, we have a special screen to these base ports where the scale, as it would come out of solution, it would try to accumulate at this bearing. So we included ports that would help remove that scale from doing that. And so we had to have another filter for that. And so we did. So what are our results? We validated it through CFD simulation. You can see at the top here, here's our traditional design. You can see this is a velocity profile. So red is bad. It means really the fluid's going fast. And that leads to pressure drop. And so with our new design, we're able to more equally distribute the pressure or the velocity, the flow in, reduce the velocity, reduce the pressure drops. And so we were able to see a 30% lower velocity, which correlates to 70% lower pressure drop. We're running this in the field. We were able to do a power study. The equipment and with the previous condition is mapped here. So this is the previous equipment's power consumption. And then with the new geo intake, the coating, that coating was also applied to the pump stages. We're able to get lower energy consumption. And so that's directly tied to keeping our pump operating at its maximum efficiency and reducing scale's impact on that. So there's a total of 18% reduction in power consumption and 3 times increased runtime. So Currently, this well is still running, going on 600 plus days. So, so the second challenge I'd like to share with you, this goes to reducing the parasitic loads and increasing efficiency for a geothermal plant. So I mentioned before, these are direct costs. This equipment's a direct cost, and so there's a lot of effort to keep the power consumption down. And so previous application was a 13 3/8 casing. We do find applications with smaller casings, but they have similar flow requests. So they're still expecting 30 to 50,000 barrels a day in a tighter casing. And so that starts to become a challenge. And so here, this is a pump curve. If you look at the left, you'll see this is head. So this is the pressure the pumps make. Red was our existing equipment. Gray is the equipment that exists in the market. And then yellow is their target range. And so in this size, they're targeting such an aggressive flow rate that really the industry didn't have, it's off optimal parameters. Basically, you don't make very much head at that flow rate. And so if we come over to the right, this is efficiency. And so the efficiency that the equipment's running in that size is significantly lower, which means much, much higher power costs. And so our challenge was for this flow rate and casing size was to develop a stage that gave better lift and better efficiency than what existed in the market. So our solution was a new pump and stage design, the SL58,000. And so it consisted of a framework, basically a bigger OD pump, but also the hydraulics design of the stage. And so we have an internal hydraulics team here. We did a sampling of our existing portfolio to see what would be a good scale candidate. And then using theoretical modeling, we scaled that geometry up. And then we inputted that into our CFD modeling and our optimization software. And so we were doing a lot of CFD evaluation of different components on the stage itself, and DOE design of experiments and optimization on some of those features. So I'll share one specific feature. So there's the direct flow pass, which were reviewed, but specifically here, these are, so this is the impeller, and flow comes this way. This is the primary flow. Well, you get secondary flow back past these seals here. And what we did is we basically optimized the length of those seals. You don't want them to be too long because then you just have extra cost, extra power consumption, but you want them to be long enough to provide an adequate barrier to recirculating fluid. And so with our CFD and DOE, we were able to do that. We added some labyrinth seal features. So these little pockets here, they basically help minimize fluid flow past this clearance. And so we were able to, comparing the existing equipment to our new equipment and the optimization, we were able to drop recirculation flow and leakage by half. So what are the results of that? I'm going to go back to our pump curves that we saw earlier. We were able to get significantly higher head out of that profile. And so this was due to two things. It was our stage design and the hydraulic optimization, but also we did a review of the well in 9 5/8 casing. The existing pumps that were being used for that were 6 3/4 inch or a 7 1/4. And so we looked at it and we did a clean sheet design for a 7 1/2 inch pump. So we're able to increase the diameter of the impeller, which is directly related to head, and then optimize it for its efficiency. And you see here's the new stage design, significantly higher head in the desired operating range. And then the efficiencies were much higher. So that directly reduces your total cost, your upfront cost, because you could put less pump in the ground. And then it reduces your total cost when it comes to operating because your power consumption is much lower. In fact, we were able to extend past the desired range and give an additional 10,000 barrels a day or so up to 70,000 barrels a day and have efficiencies of 83%. So So to summarize, I wanted to share ESPs do have a role in geothermal production. The technology is directly applicable. I just wanted to raise some concerns for the community to think about. If there's different ways to address this. These were in the production string. Things that can be done is to review your casing size to make sure that the production you want is available. And perhaps go with a bigger casing if you want certain style flows. Scale management, perhaps we could have had a deeper well, so that way we have higher intake pressures and you don't have the presence of scale. It doesn't come out of solution until after the equipment. So there's just things to think about, and I wanted to share. So Halliburton has it's a little known fact, but we've been in the geothermal market for 70 years, and so we have this through the whole life cycle of the well. Today, I focused a lot on the operations side, but we have competencies on the drilling evaluation side as well. So with that, I'd like to return it to Susan for Q&A.
Thank you. That was great. And we've had a lot of wonderful questions. And I just wanted to mention too that one thing that fascinates me about what both Fervo and Halliburton are doing is they're using a lot of technology that was developed in oil and gas operations and in those areas and finding out where they can be adapted and modified. And I think that that's one of the interesting things that's been going on with like the Geode project, et cetera, is just the whole idea of fast accelerating development of geothermal by using all different kinds of technologies possible, in addition to using geological tools, for example, reservoir simulation and characterization, et cetera. So I just want to point out that there's a lot of crossover potential. And that said, we've had a lot of questions. A lot of them have been answered. Josh and Gabe, if you want to turn on your cameras, and also Nicole, we can answer some questions. But one of the questions that was answered that I thought would be worth talking about was one that was posed by the Osage Minerals Council, talking about repurposing a well, but it was a well that was drilled to 8,000 feet, 4,000 feet into granite. And so what is the potential for converting something like that into geothermal?
That's a great question. And I think I answered that one, but happy to answer it again live. It really, obviously geology is important, but one of the main contributing factors to if that well would be economic for EGS is what temperature does it reach at that 8,000 foot mark. So that's the reason, that's one of the reasons that we're drilling to that depth at Cape, is because that's the temperature that we're looking for to produce our ORC units with, our binary power plant. And so that would be the main question, is what temperature does it reach at that depth? And then there's well construction considerations as well. Geothermal wells require typically higher flow rates than oil and gas wells. And so we usually use larger diameter casings. And so, yeah, how small of diameter casings are present in the well would also be something to consider. So definitely, it's not out of the question, but it'd be there's definitely worth talking about. So yeah, feel free to reach out and we can keep discussing.
And kind of a related question, and this is for all three of you. What is it like to drill through granite these days?
What's it like to drill through granite?
What's it like to drill through granite these days? Have there been a lot of advances? Is it faster and easier than it used to be?
I think so. At Fervo, we use we're making use of PDC bits, which has given a lot of advances in terms of higher ROPs, And yeah, we've learned a lot as we've drilled more and more wells in granite, especially the horizontal wells. There's a great paper. I didn't include it in my references, but it was part of the Stanford Geothermal Workshop. It's by El Sadi et al. 2024. And it has a really great description of the Fervo learnings as we've drilled through this granite reservoir. But yeah, it's definitely improved from even when we first drilled our first well. So yeah, I don't know if Josh or Nicole have any comments on that.
I think you answered it pretty well. I mean, you just have to think, I'd say we do well studying and see if there's any of the issues I provided regarding an already existing completion.
Okay, perfect. Well, here is a top-rated question that just slipped off my screen. There it is. So, top rating question. What subsurface information did Forge have when they drilled their exploration wells? What was the exploration risk of not finding economic quantities of heat?
Great question. So they actually had, most of the information that I shared. They had just fewer gravity stations, but they had the MT data. They obviously had all the seismic data. They had their own gravity survey. They had even other data sets that I didn't even talk about, that we also integrated. But obviously the one thing they didn't have was a really nice and detailed offset well, less than, approximately a mile away from their development. So, that was a really a huge benefit for Fervo in selecting that site, for our first, large scale project. And so the exploration risk for Forge, I mean, I would say was slightly higher, because you were sort of extrapolating further from Blundell, but you still had that anchor of measured temperature in the middle of the basin at Acord 1. And so I think the question for them was not whether they would hit it, but sort of exactly where they were going to hit it. And so they drilled vertical, sort of confirmation wells before they drilled they don't drill actually horizontal, but they drilled highly deviated wells for their producer and injector. But they drilled vertical wells to confirm exactly where they wanted to sort of site their highly deviated section, to help confirm that temperature. So I would say they still had, a good sense relative to some other more greenfield prospects.
Great. Okay, so we have time for one or two of these upvoted questions. So Terry Eskner asks, how do you characterize a bench in granitic rocks? Is it a temperature bench, a lithologic, or something else?
Yeah, that's a good question. It's more of a temperature bench, and so yeah, you're trying to keep each bench at more or less a relatively constant temperature, and then you step down to the next bench and you're accessing a different temperature, higher temperature. It's all within this granitic unit. If you were doing it somewhere else where there were actual lithologic controls on your bench, that's possible. But at Project Cape, it's temperature driven.
Well, so I have kind of maybe a dumb question, but okay, if you're talking about high heat and it's been high for a while, is any of this granite metamorphosed?
There is some sort of, there's alteration sort of at the very top, kind of at the contact between the granite and the basin fill sediments that we've observed from our mud logs. But the granite itself, is not metamorphosed, although there is an older the granite is tertiary in age,
Okay.
and it's actually intruded into a Precambrian gneiss. So I didn't get into that. But the forge wells have encountered it. It's really hard to distinguish in cuttings the gneiss from the granite, but Forge has done some cores and observed the gneiss, and so and you can observe it in the mountain range there.
Oh,
So
how
there is
super
some
interesting.
older metamorphism. Yeah.
Well, that's really interesting. Wow, so many more questions and so fascinating, especially when we get into just the nature of the, I would say, not ore body, but the granite. But it's almost like the nature of the reservoir. Anyway, I want to say thank you, a big thank you to Nicole Wagoner, Gabe Matson, and Joshua Webster. This was a great webinar, and see lots of hearts and celebratory emojis coming up. And just want to say thank you and happy Geothermal Day. So if we didn't, and also just in the chat, if we didn't get to your question, please send an email to education@aapg.org. Thank you.